Greetings everybody and welcome back to another video. Today we got a complex analysis snack, nice little treats for the complex analysis fans out there. Yeah, I'm pretty much done with uni now, by the way, because I finished exams like almost a week ago. Hopefully I passed all my exams because I think I flopped like 2 of them, so I really don't know how I did with those ones at all. Assuming that I passed everything, then that's pretty much it for this degree, which is pretty cool. So I'm jumping right into Masters next year for the next 2 years. That also means that I have all the free time that I want now, between now and then during the summer. So maybe that means more YouTube videos, I don't know. We'll see though, because yeah, my schedule's always all over the place, so it depends on what I feel like doing, but yeah. What are we doing today? We're taking a look at this integral from 0 to pi of logarithm of sine of x. And if you're a long-term viewer of this channel, if there are any out there, then you might recognize this because I actually did this integral like 1.5 years ago. It's ages ago. And yeah, that's somehow like the 3rd most viewed video on my channel. I don't know how that got that many views. What was the approach we used for that video? We used this sort of rectangle contour and we push this all the way up to infinity and we recover that integral somehow. It's a bit of a convoluted approach. It's pretty cool though. So if that seems interesting, I'll put a link in the description and you can check it out if you want to. But yeah, the approach I'm going to show today is a lot more elegant in my opinion. Someone posted this solution actually on that video, and I think I saw also on a few places on Stack Exchange, and it's a lot nicer because you only got to evaluate one integral instead of like 6 path integrals that we had to do in that previous video. That ended up being like a 30-something minute video probably. How can we get started with this one? Well, first of all, notice we're going from 0 to pi, and if you take a look at the terminals there, if you plug 0 and pi into sine of x, then you get a 0. But logarithm of 0 is undefined, so that might be a bit of a problem. Turns out though that this integral converges, which is quite nice, but I'm going to do a bit of a safety precaution anyways. I'm going to take a limit. So we're going to rewrite this as the limit as epsilon approaches 0 of integral from epsilon to pi minus epsilon of the logarithm, and then I'm going to rewrite the sine of x in here in terms of the complex exponential representation, and that's going to be e to the I times x minus e to the minus I times x, and this is all divided by exactly 2i. Okay, and we can finish off with a dx there, so nice and fine so far. I should probably also define the branch of the logarithm I'm working in, so we'll just take the principal branch because that seems to work out just fine. So that's going to run from negative pi all the way up to pi. Okay, so what I'm going to do from here, I'm going to start breaking up the logarithm a little bit because there's a lot of stuff going on in there. I'm going to use, I think it's the quotient rule or something for the logarithm. So let's do that. So this is going to be the limit as epsilon approaches 0 of integral epsilon to pi minus epsilon. We have the logarithm of e to the I times x minus e to the minus I times x. And then we have minus and then the thing on the denominator. So that's going to be the logarithm of exactly 2i. Now, you could put a dx there, but you also got to be a bit careful whenever you work with logarithms and complex numbers because you got to deal with the branch cuts and everything because they might, yeah, they're just confusing in general. Whenever you work with logarithm properties, like so, logarithm laws whatsoever, you also got to add an extra offset of 2 pi I times k, where this k over here is an element of the integers. Yeah, reason why is because sometimes when you multiply complex numbers together, the arguments might go outside of the predefined argument that we had up over there. You also got to add this offset just to, you know, return it back to the proper arguments, if that made any sense at all. So yeah, we just got to add this extra offset over here. We also got to figure out what on earth k is because we kind of want a value for this integral, not something that depends on what branch we choose. That would be a little bit funny. How do we get the value of k? Well, notice that k is pretty much directly linked to the imaginary parts. So maybe if we just compare imaginary parts of what we have over here on this line and the imaginary parts of what we had initially, then we could deduce the value of k from there. The nice thing with logarithms though, if you want to calculate the imaginary part, you just take a look at the arguments because hopefully you know how to rewrite logarithms of complex numbers. Log of z, the real part is just the logarithm of the absolute value of z, so this is the real part over here. And then you have a plus I times the argument of z. So arg of z is the imaginary part of log of z. So if you want to calculate the imaginary part of a logarithm, just take a look at the arguments of the thing inside. So what's the argument of sine of x going to be? Well, x is varying between 0 and pi, which means sine of x is always positive, so the argument is, yeah, just 0. So the imaginary part up over here is precisely equal to 0. Okay. And how to get the imaginary parts down here? Well, we already got the imaginary part of that 2 pi I times k. So the imaginary part of this logarithm is just the argument of e to the ix minus e to the minus ix. So how to get that? Well, just think of it on the argument plane. X is between 0 and pi. So that means some generic e to the ix would probably look something like this over here. And e to the minus ix would look something like this. So this is e to the minus ix, e to the ix. So what happens if you take the difference between these two? Well, we just take this vector, reverse it, add it onto the tip of the other arrow, and you actually land right back onto the imaginary axis. So that means the argument of this guy over here, or the imaginary part, is just going to be pi on 2. Right? And how about logarithm of 2i? Well, 2i is living somewhere up over here as well, so the argument of that thing is also pi on 2. And then we also have a plus the argument of this thing, or the imaginary part, is just 2 pi k. Okay? And we want this whole thing over here to be equal to 0. Alright, so what's the value of k we should pick? Well, it's pretty obvious. K should be equal to 0. So that means we can just forget about this. So k equals 0. Alright. So we're good to move on from here, so we can just break up this logarithm without any problems, without having to include an extra offset there. Okay, so next thing I'm going to do, we have 2 exponentials in here. I really want 1 exponential instead of having to deal with 2. So what I'm going to do is I'm going to factor out one of those exponentials, and I'm going to choose to factor out e to the ix. Why not? So this is going to be the limit as epsilon approaches 0. Integral from epsilon to pi minus epsilon. We have the logarithm of, I want to factor out, e to the ix. So that leaves us with 1 minus e to the minus 2 times I times x. And then we have a plus logarithm of e to the I times x. And then we also have, that should be, it's there. No, we have minus logarithm of 2i still. Right? But because we did the splitting over here, whenever we use a log law, we got to introduce an extra offset of 2 pi I times. So this would be a k1 over here. These are different k's, by the way, so maybe I write this as k2. So what exactly is k2 going to be? Let's investigate that a little bit. Well, this is also a dx over here. How can we get the value of k2? Well, this 2 pi I times k2, this part over here really came from this logarithm over here. So we're just going to compare the imaginary part of this logarithm with the imaginary part of these logarithms, and also the imaginary part of this part over here. Okay, well this one's a little bit more tricky to work with because we can't just directly extract the arguments of 1 minus e to the minus 2ix. But what you can do is you can just plug in some value for x in the interval we're working with, and then just solve for k2 from there. And a nice value to put in for x is, let's take x equals pi on 2. So what happens if you take x equals pi on 2? Well, you're going to get e to the minus, well, that's just going to be minus I times pi, I believe. But e to the minus I times pi is exactly -1. And then we got 1 minus -1, which is 2. So the argument of this part over here is precisely equal to 0. And how about over here? Well, this is going to be e to the I pi on 2, which is I. And the argument of this thing is just going to be pi on 2. Okay, and what's the argument of what we had before up over here? Well, plugging in x equals pi on 2, we're going to get I, and then minus -I. Hopefully you can see why. So that's just going to be 2i. So the argument of what we had up over here is just going to be, pi on 2. So we want pi on 2 to be equal to 0 plus pi on 2 plus, that's going to be 2 pi k2 there. Okay. And because we have pi and 2 over here, those kinds of cancel. That means k2 must be equal to 0. So we can just get rid of this guy just like before. So once again, we can break up these logarithms without much problem at all, assuming we're on the principal branch. Okay, if you're not on the principal branch, then you probably need to introduce some extra correction terms over there. Okay, so now once we have that, we can rewrite this further. So this is the limit as epsilon approaches 0 of the integral from epsilon to pi minus epsilon. We have the logarithm of 1 minus e to the minus 2 times I times x. Okay, and we can actually start breaking up the integral. So we have just these parts over here, which aren't too bad to work with, because this over here is just going to be I times x. What's the integral of I times x? It's just I times x squared on 2. And we can just plug in the limit of these terminals over here, which is 0 and pi. So that's not too bad because this is going to give us a plus I and then pi squared on 2, I believe. Yeah, so that's x squared on 2, we plug in pi. And then we also have minus x times the logarithm of 2i, but that's just going to be, yeah, minus pi times the logarithm of 2i. And what's the logarithm of 2i? That's just going to be log of 2 and then plus I times pi on 2. Because this is the real part of the logarithm, that's the imaginary part of the logarithm, that's I times, yeah, the argument of I, which is pi on 2. So if you actually expand this, you get minus pi log of 2, that's actually the answer to this integral. And then you also got minus pi squared on 2 times I, which nicely cancels out, and I lost yellow chalk, which nicely cancels out with this part over here. So I got some nice cancellations there. So yeah, that's pretty much that. So I'm just going to rewrite this again one more time. Okay, so we've come quite far already. We nicely reduced it down to this form of an integral where we have, yeah, pretty much just this integral left to evaluate. So if you just take a look at this integral, notice that we're going from epsilon to pi minus epsilon, or pretty much just 0 to pi. And if you take a look at this e to the minus 2ix over here, you might realize this is actually tracing out the unit circle in the complex plane. So let's draw that. So we can actually turn this into a contour integral, which would be quite nice. In particular, if we just let z be equal to e to the negative 2 times I times x, and we can do a little substitution over here. So in particular, we have dz, and that's going to be equal to minus 2i times the same thing. So yeah, minus 2i times the same thing, which is just z, and then times a dx. So in particular, if we do a substitution down there, we have our original integral I, or let's just call this integral over here, because I don't want to write out everything really. Let's just call this integral, let's just call it j. You can't even see that j, yeah, j over there. So what's j going to be equal to? J is this going to be some kinds of contour integral. I don't think it's a proper contour integral. Let's just call it some contour integral. Let's just say some path integral over gamma parameterized by epsilon. We have the logarithm down there. So we have, yeah, logarithm of 1 minus that e to the minus 2ix, that turns into a z. So we have a z over here. Then we have our dx over here. And dx is just going to simply be 1 over 2iz. So we can bring, yeah, negative 1 over 2i up the front and divide this whole thing by z, and we integrate with respect to z. Okay. And now, instead of considering, this is really the integral after, let's sketch out the path gamma epsilon somehow. So in the complex plane, what would that look like? Here's the complex plane, once again. Gamma epsilon, well, we're starting at, well, this is e to the minus 2ix. So that means if we start at epsilon, we're going to be down over here. And if we go to pi minus epsilon, we're going to end up over here. So this path is our path of gamma sub epsilon, and we really kind of want to turn this into a contour. So usually, just like with integrating on the real line and whatnot, complex analysis, those sorts of examples, this is the interval we want to recover. We want to turn it into a contour, so we kind of want to close off the gap over there somehow. But the problem is there's going to be two singularities. There's a singularity at exactly 1 because of the branch points there. Because just look at this logarithm, we have, if z equals 1, we get a branch points. So we get a branch point going off this way, I believe, because it's 1 minus, so it reflects the branch cut that was going on the negative x-axis to the positive x-axis. And also, we got a removable singularity at 0, because of the z here. So there is a singularity at 0, but it's removable, which means everything's holomorphic in here. So how can we close off this contour? We can just introduce some kinds of curvy path in over here, and we might as well call that little path in that gamma sub epsilon. Okay, and we'll call the whole entire contour C. Alright, so this integral that we want to evaluate, this is precisely equal to minus 1 over 2i. This integral gamma epsilon, big gamma epsilon, well, that's going to be this contour integral over here. So contour integral over C, and then we want to subtract off the integral over little gamma epsilon, which we can, yeah, make it go around that way. So we'll just subtract off the integral over gamma epsilon of the same function, right? So logarithm of 1 minus z over z dz. I'll just factor out the integrals, use that silly notation there. Now, what's the contour integral over C going to be? Well, because everything is holomorphic on the inside, by Cauchy's integral theorem, this part over here just vanishes off to 0. So pretty much now, we're left with 1 over 2i integral gamma epsilon of, this function. So we just got to evaluate this integral now and take the limit as epsilon approaches 0, and then we are pretty much done. By the way, we're trying to show that the j integral goes to 0. So, how can we do this? Well, let's introduce a parameterization. What's a nice parameterization for little gamma epsilon? So on little gamma epsilon, we can parameterize as follows. We can rewrite z as being 1 plus, and then we have epsilon e to the I theta. Right. And theta is going from, looks like it's pi and 2, all the way down to 3 pi and 2. Technically, maybe you have to introduce some extra delta in there, but we're taking limits anyway, so it doesn't really matter. And then we need to calculate dz as well. So what's dz going to be? dz is just going to be, chain ruling this, I think that just gives you I times epsilon e to the I theta d theta. Okay, so if you plug everything in now, what do we get? We get 1 over 2i integral from pi on 2 all the way up to 3 pi on 2, and then we have the logarithm of 1 minus this stuff over here, which is just going to be negative epsilon e to the I theta, and then we have divided by, what's z going to be? Well, it's just going to be 1 plus epsilon e to the I theta, and then dz is just going to be I times epsilon e to the I theta, and then d theta. Now we wanted to show this guy goes to 0, so we need to estimate it. So yeah, I'm just going to get rid of that 2i out over there because it's not really helping that much, and I'm going to put absolute values everywhere. So what happens if we estimate this? Now we can use the integral inequality to start off with. So this is less than or equal to integral from pi on 2 to 3 pi on 2. And how do we estimate this numerator over here? Because we can pull the absolute value inside of the integral now. Well, logarithm of complex number can be rewritten as logarithm of absolute value of complex number plus I times the argument of that complex number. So let's write that out. We have the logarithm of magnitude of the inside. What's the magnitude or the modulus of the inside? It's just going to be epsilon. Epsilon's a positive number. And then we have, plus I times the argument of the inside. Now the argument of the inside, I don't want to go too much into detail because it's probably not really worth it. It's going to be bounded by some, big theta over here, some big theta constants. You probably have to put this minus into this e to the I theta somehow, which I really don't want to do. And the maximum of the theta is just going to depend on these bounds here. It's just going to be some fixed theta constants over here, so that's fine. And then you can use triangle inequality on this because there's still absolute values out over here. And triangle inequality, allows you to get rid of this I. And so numerator is bounded by log of epsilon plus some kinds of big theta constant here, which we don't really care about. And then how about the denominator? Well, we can use the reverse triangle inequality on this. We can rewrite this as 1 minus negative the thing. So this is absolute value of 1 minus epsilon. But if epsilon is small enough, you can forget about those absolute values there. So it's just going to be 1 minus epsilon. Okay, and then we have absolute value of the I, which is this one, absolute value of epsilon, which is, epsilon, and then absolute value of e to the I theta, which is just 1 once again, so this is integrated with respect to theta. So now notice that everything we have inside of the integrand is theta independent, so we can, in particular, pull all this stuff out and just take the limit on the outside. So what happens in the limit as epsilon approaches 0? Well, this epsilon goes to 0, so you're just going to be left with 1 minus 0, which is 1. And then you can calculate the limit of epsilon times log of epsilon. Hopefully you know that result. It's just going to be 0. And then you have epsilon times big theta. Theta is finite, so you're just going to get 0 anyways. Then 0 times the integral, which is some number, I don't know, a. So this is just going to give you 0. Okay, so in the limit as epsilon approaches 0, this integral, or the modulus of this integral that we have over here approaches 0, which means the integral itself approaches 0, which means that this integral gamma epsilon over here in the limit approaches 0, which is quite nice. And, well, that means that the integral j that we were after before, that also approaches 0. So this is bye-bye over here, and what we're left with is this negative, I dropped the chalk, negative pi times the logarithm of 2, which is the answer that we had from 1.5 years ago. So yeah, that's another approach. This took a lot longer than expected, probably because I spent too long explaining the argument and stuff over there. That's a pretty cool approach. I kind of like this one a lot more than the other one. Hopefully you guys liked it as well. And if you did, make sure to subscribe if you want to see more content like this. I'll probably post some more complex analysis snacks over the holidays as well. Up until the next one, hope you guys have a wonderful day. I'll see everyone in the next one.